today. Okay, this is week 4 of high school chemistry. I'm very excited to get started this week. We are going to talk about molar mass this week through a lab and mole ratio. We are going to do a lab called the mole ratio, and we're going to talk a little bit about elements and atoms. We're going to set ourselves up for balancing equations next week in class. Unfortunately, next week is going to be not as fun of a class. We're not going to do a lab, which is a very important part, but not all that exciting, part of chemistry. So today we are going to get started. I did look over everyone's homework assignments, and the 2 that were turned in were great. Cami, I got yours. I just finished grading it. The just general comment I would make to all of you on your lab reports is that make sure before you upload them, you reread them. One of them this week they were just in the wrong order. It looked like almost you cut and pasted, and it pasted back into the wrong spot. So just make sure before you hit that upload button, you guys just go through, look for any quick spelling checks, spelling errors, any quick formatting errors. For the most part, these lab reports have been great. I'm very impressed with the work that you guys are doing, and I have no issues with them. So I'm very, very pleasantly surprised. Great job. Last week in class, we did talk about the different phases of matter and the different ways that matter can change. So what I wanted to do was just kind of review that at the start of this class. So if we can go ahead and look at our whiteboard, I'm going to draw one of the phase change diagrams. And maybe we could go ahead and label this the best that you can. So over here we have temperature. And we're just going to do a generic one. We're not going to do, that's not a very good picture. We're not going to do specific, like we talked about water, you can actually add temperatures there. So why don't you, Cami, go ahead and see if you can label any parts of this diagram for me. Unfortunately, you're the only one here, so let's see what you can come up with. All right, you certainly are on the right track here. Awesome. Perfect. Exactly what we would be doing. Now, when a matter goes from a solid to a liquid, what is that called? Can we add that up here? Let's see if I'll make a little chart over here. And we'll go solid to liquid, liquid to gas, gas to liquid, liquid to solid. Let's see if you can add any of those terms. So you put up solid to liquid already. I'll add it over here. You put melting. All right, can we put anything up when a liquid goes to a gas? You can either put it right on the phase change model, or you can go ahead and put it over in this side box. It's up to you. Liquid to a gas, awesome. It's evaporation. I'll add that. You can just write it right next to the word text if you want. It can be pretty tricky to get rid of that text word. Sometimes it does not cooperate very nicely with us here. Freezing, perfect. I'll add that over here. And now this last one is the one that I always find the hardest to remember. I think because it's the one that I think about the least. Neither can I normally. However, I've got this one today. Gas to, sorry about that. Gas to a liquid, we have condensation. All right, great job remembering the rest of those by yourself. This was supposed to be a group effort, so there should have been helpers helping you there. I'm very impressed that you were able to get all of them by yourself, with the exception of that one. So that's a great phase change diagram with the names of what the change is: the melting, the evaporation, the condensation, and the freezing. Check plus for you today. All right, so what we are going to talk about today is we're going to talk about elements and atoms. This is kind of a two-part for this week and next week. So if you could look at your PowerPoint screen. We are going to go there. So a little bit of a refresher on matter. Matter is anything that takes up space and has mass. Last week we talked about how matter changes. The week before we talked about what matter actually is. So all matter is made up of atoms. And that's kind of what we're going to focus on today, those smaller atoms that make up matter. Atoms are the building blocks of matter. They're sort of how bricks are the building blocks of houses. Okay, if you're building a brick house, you need to place individual bricks in a spot in order to create the whole house. If you are making matter, the atoms are the individual pieces that together form whatever the matter is that you are making. And just like bricks of a house, if you arrange them certain ways, you know, if you have 50 bricks and you make 2 stacks 25 high, you'll have a nice tall structure. If you make 5 stacks 10 high, you'll have a shorter structure. Atoms are the same way. Depending how they are put together, they will build different things, or different types of matter. So there are 3 parts to an atom. This is probably something that you know, but I just want to double check. We have protons, which are positive. You have neutrons, which have no charge. And you have electrons, which are negative. The way I remember this is pro, and the start of proton is positive, and nu is neutral for neutron. The protons and the neutrons are found in the center of the atom at the nucleus. In the picture that I have on the screen here, the protons are yellow, the neutrons are the orangey color. The orange and yellow together are the nucleus. And around that, those 2 little circles with the small white circles, those are the electrons. Those electrons are orbiting the nucleus in valence shells. So what exactly is an element? Well, elements are the alphabet to the language of molecules. To make up molecules, you must have elements. Just like to make up words, you have to have letters. Okay, in order to spell the word elements, You need the E, the L, the E, the M, the E, the N, the T, the S. In order to make up water, you need 2 hydrogens and an oxygen. It's what forms it. So elements are made up of atoms. While the atoms might have different weights and different organizations, they're all built in the same way. They all have protons, they all have neutrons, and they all have electrons. There's a couple general rules. Atoms always have as many electrons as protons, and atoms usually have about as many neutrons as protons. So here is a diagram of hydrogen, helium, and carbon, and the number of protons, neutrons, and electrons that each of those have, how they are arranged. So if we look at hydrogen, it has 1 proton, the yellow, 1 electron floating on the valence shell on the outside, and it has 0 neutrons. Helium has 2 protons, 2 electrons, and 2 neutrons. And carbon has 6 protons, 6 electrons, and 6 neutrons. Now, if you add a proton to any of these, you get a new kind of atom. If you add a neutron to any of these, you get an isotope of an atom. Now, if you added a proton to hydrogen, you would have a new element. If you added one to a neutron, you would just have a different isotope. Some isotopes are radioactive. Basically, an isotope is just a different version of the element. So a little bit more about elements. You want to go ahead and read this one, Cami?
Sorry, my voice is kind of still scratchy from this morning. Okay, but it says more about elements. Elements are the building blocks of all matter. The periodic table is a list of all the elements that can build matter. It's a little like the alphabet of chemistry. The periodic table tells us several things.
All right, great job. Oh, no. So the periodic table can tell us a couple of things. If we look at a periodic table, which I have and we're going to put up in a couple of minutes, this number on the top is the atomic number. That's the number of protons. The O is the symbol for the element. Some periodic tables have the element name, some do not. And then at the bottom, there's a number, and that's the atomic mass, or the atomic weight. That's the number of protons plus neutrons. So let's go ahead to our whiteboard, and we're going to look at a periodic table. Ugh, that didn't work very well. All right, give me 1 second to get a better picture up here. No problem, Ethan. I'm just trying to get a periodic table to upload. It should just be one more second. Why is this not working? All right, it's telling me it worked, so let's check it out. Yeah, I want it in here, though. Okay, so go ahead, back up. Get rid of we were on the whiteboard, but let's go look at the PowerPoint screen again. Instead of a PowerPoint right now, you should see a periodic table. So if you go ahead and you look at your periodic table, and it's really still not big enough. All right, I'm going to have to redraw one of these for you guys. All right, go back to your whiteboard. I'm going to redraw one for you here. So here we have a square of our periodic table. Okay, what I would love for you guys to do is tell me the atomic number, the atomic mass, the number of protons, number of neutrons, the number of electrons. All right, and I know you just joined us late, Ethan, but if you know any of these, if you could add them in here, and I'm going to kind of separate it for you guys. And if I could have Ethan, you write your answers here in this column. Cammie, if you can write your answers in that column, that would be fantastic. This is for nitrogen. All right, Cammie, you got that correct. Okay, so we'll just go over real quick the number of the atomic number, Ethan. And I'm going to go ahead and draw some arrows here. The atomic number is this number right here that I'm highlighting in yellow. And it is equal to this number 7 right here that I'm highlighting in yellow. Then we have our atomic mass. And the atomic mass, we'll change highlighting colors here, is going to be orange. And in our periodic table, it is down here. Now our number of protons is equal to our atomic number, so we can color that in the same because it's going to be that number. And our number, here's kind of where you have to do a little bit of math. So I'm going to write it down here. The atomic mass, which is orange up here, so that bottom number, is equal to the protons plus neutrons. So in this case, 14 is equal to protons, which is 7, plus our neutrons. We would solve this just like we were solving a simple algebraic equation. In this case, the neutrons is equal to 7. It's not always going to work out that way. And of course, the element that I picked, it did. And we know that atoms usually have the same number of electrons as protons. So, with that being said, we're going to try a different one. I'm going to erase your numbers, Ooh, not what I wanted to do. All right, Cami, I'm going to see if I can erase your number. I couldn't. All right, so we are going to go ahead and try this again. And we're going to see if we can get this. We are going to have the atomic number. We are going to try the atomic. I'm going to put a new symbol up here. Atomic mass, the protons, neutrons, and electrons. And our new symbol is going to be fluorine. Fluorine so if you guys could go ahead and try to figure that out, that would be fantastic. All right, it looks like, Ethan, you just need to fill in the neutrons. So there we go. Okay, so how do you decide the number of neutrons? You use this little formula at the bottom here that hopefully you can see me pointing to it with my laser pointer. Down at the bottom left, the atomic mass, which is 19, is the protons plus the neutrons. So we're going to fill in a simple algebra formula. And for us, I'm going to do it over here on the right-hand side. So here we're going to do the number of neutrons for fluorine. Okay, and we have our atomic mass is 19 equals the number of protons is 9 plus the number of neutrons, and we're going to just call that N. So now if we're solving for algebra here, we need to get all of our numbers on one side, and we need to get all of our variables on one side. So to do that, we're going to subtract 9 from each side. So we'll do 19 minus 9 equals 9 minus 9 plus n. So 19 minus 9 is 10 equals 9 minus 9 is 0, neutrons. So the neutrons is equal to 10. So this is what we have. Our atomic number, both of you got perfect. It is 9. Great job. Our atomic mass should be 19. The atomic mass is that number that's written on the bottom. Protons, 9. Perfect. It's the same as our atomic number. Electrons is the same as protons. Perfect. And our neutrons is 10. All right. Great job. We're going to try one more of these, and hopefully we will get it with no problem here. All right. So let's get our last one up here. We have the atomic number. We have the and our symbol we're going to do is argon, or element. So here we have argon. Argon is one of the elements that actually has 2 letters that make up its symbol. It's Ar. And it has a 18 here and a 40 there. All right, so go ahead and try to figure this one out. All right, go ahead and try to figure this one out for us. All right, so let's go ahead and take a look. We have the atomic number equaling 18. You both have that. Great job. Okay, we have the atomic mass equaling 40. You both have that. Great job. Remember, the atomic number is right there on top. The atomic mass is right there on the bottom. You're just transposing it, transcribing it, whatever you want to call it. You're not doing any math to figure those out. Then we have the number of protons, 18. Awesome. That is equal to the atomic number. Good job. We have the number of electrons is equal to the atomic number. Great job. And then we do the simple formula to figure out the number of neutrons, which you both got here, which is 22. Fantastic. Okay, I'm just sending a quick poll. Let me know if this makes sense to you guys and you're ready to move on, or if you'd like to go ahead and do another example. Completely up to you guys. I want to make sure you're understanding it before we go on. Okay, so we're going to go ahead and do one more example. Let me go ahead and pull one more element up here. This time we'll do the element lithium. All right, and this time I'm going to do it a little bit different. I don't want you guys to write your answers up here on the whiteboard. Okay, here's the element. The element symbol is Li for lithium. Okay, so I locked your whiteboard so you cannot write on them. Okay, right now, what I want you to do is go ahead and answer, what is the atomic number? On your screen right now, make the whiteboard smaller so you can see the 4 screens and you can see the one with my picture on it. Right below my picture, there is one that says, we haven't used. It might have a map in it right now. What I want you to do is go to the second icon on that toolbar, and it looks like a yellow notebook. Okay, and I wrote in there, it says, what is the atomic number? Go ahead and answer to me. You're going to have to hit Add Note. And go ahead and type your answer in. And it still came up there. All right, perfect. Okay, I was hoping you wouldn't be able to see each other's answers. Can you see? Can you guys see what each other wrote on the notepad, or can I just see both of your answers? Can you only see your answer, or can you see that you both answered it? Okay. Fantastic. All right. Awesome. So here's the next question. Okay, what is the atomic mass? Go ahead and give me your answer, the atomic mass. Awesome. Okay, how many protons are in lithium? All right, how many protons? Great job. Okay, next, how many neutrons are in lithium? Awesome. Good job. And the last one, how many electrons are in lithium? Awesome. Fantastic. That was just a good little way for me to check to make sure that you actually understood it and you weren't looking at each other's answers. Great job. You both got them 100% that time. Perfect. If we have time, we'll review this a little more at the end of class, but I think for now you've got it. So let's go ahead and click back on our PowerPoint screen, and I would make it larger again if I were you, because it just makes it easier to see. When you're talking about models of atoms, there are two main types of models that scientists use. There have been lots of different types, but these are the two that are accepted as correct now. And they are the Bohr model and the Lewis dot structure. So the Bohr model looks like this. It's what I showed you in the beginning. The Bohr model shows all of the particles in the atom. In the center is circles. Each circle represents a single neutron or a single proton. With that being said, the Bohr model is great when you're doing elements with small atomic numbers. Oxygen, argon. When you start doing elements with large atomic numbers, gold, it gets very hard to do the Bohr model because there's so much information on the chart. Protons should have either a plus or a p. In this case, they have a plus in them. And neutrons should be blank or have an n. In this case, they're left blank. Then you have a circle around the nucleus that are the electrons. The electrons should have either a minus sign or an e. In this case, I put the charges up here. Now, there are a few special rules when you are writing electrons in a Bohr model. When you are writing electrons in a Bohr model, you can't just throw all of the electrons on the first orbital of the element. The electrons live in valence shells or energy levels. So only so many can be on a certain shell or on a certain circle. So let's take a look at this. Here we have the nucleus in the center. Okay, that's the shaded gray area. That would be where your protons would be. And your neutrons. Then you have your first shell, that next circle out. That can only have 2 electrons in it. Your second shell can have up to 8 electrons in it. And your third shell can hold up to 18 electrons. Generally speaking, you're not going to draw anything past that. Okay, at that point, you're at 28 electrons. That's lots of dots that you're drawing. Go ahead, Ethan.
Is there any, hang on, one minute. Is there any atoms with 18 on the third shell?
Yep. None of the ones that we're going to do today for examples, because I figured that was kind of overkill on drawing, but yes, there are. So let's go ahead and let's take a look at some special rules. Okay, you can't just shove all of the electrons into certain orbitals. You start at the beginning and you work your way out. The electrons on the outermost shell are called valence electrons. Okay, so we are going to try lithium, the same one that we just figured the atomic number out of. Okay, and lithium, I'm going to put this on the whiteboard for you guys. So, oh, lithium's already there. Perfect. So if you flip over to your whiteboard, we'll be able to see this together. So here is lithium. We are going to try to draw the Bohr model for lithium. Now, I'm going to give Ethan a block. And I'm going to give Cami a block. So, make them a little bit more even. I would like you to try to draw what you would do. Right? I just unlocked your whiteboard, so you can now draw. Now I'm going to go ahead and draw mine over to the right. Now it's hard on the whiteboard to draw. I understand that. Okay, and you may actually find this way easier to do on a sheet of paper. If you want to do it on a sheet of paper to practice, that's perfectly fine too. When you're working with the whiteboard, that adds a whole nother element of trying to get it to work correctly. And the right-hand side, you see mine, which is what you should have. Okay, the first thing you need to do as you're drawing is you need to figure out the number of protons, the number of neutrons, and the number of electrons. So protons we know are 3. And we know that our protons are equal to our electrons. And then we use our little algebraic expression. And we find the rest out. So that is what you should have. Now, I will be honest, it is very difficult, like I said, to draw up here on this whiteboard. Okay, so we are going to try another one. Ethan, go right ahead. Do you have a question?
Shouldn't there be 4 neutrons instead of 5? Because 7 minus 3 is 4.
You are exactly right. I wrote 4 over here on the left, but I drew 5. Exactly right. Good catch. Now the trick will be if I can get only one. Perfect. That is what it should look like. Thank you very much for pointing that out to me. Okay? So fantastic. We are going to try one more, and then we are going to go ahead and do our lab for today. So the one we are going to try is, we are going to do, let's see, nitrogen we'll do. So nitrogen 7. All right, so let me erase everyone's. Okay, so go ahead and if you could just put it in the same spot We'll do. That would be fantastic. All right, great job, guys. There are 7 protons, 7 neutrons, and 7 electrons. So there should be 7 electrons in the valence shells. And then there should be 7 protons and 7 neutrons in the nucleus. Now, if you look at the difference between yours, I just want to point this out. Ethan did his a little different. It is absolutely correct. He just put his nucleus in its own little circle, so that is perfectly fine to do. As you have elements with larger atomic numbers and atomic masses, that's probably going to be even more important so that your diagram stays neater. Okay, so we are going to go ahead and get started on our lab for the day. If we have time, we will go ahead and try a couple more of these. Otherwise, as I said, next week is going to be not a lab week, so we are going to work more on some math. I would definitely recommend for next week that you guys have a calculator. You have some scrap paper. It will be much easier to work on your scrap paper than it's going to be to work on the whiteboard. So let's take a look at today's lab. We are going to be doing in your lab book, lab number 4, which is on page 26. So the materials you need are the 96 well reaction plate, your plastic toothpicks, and your small beaker, along with 4 of your reagents. Go ahead and get your stuff out next to you. Put your lab safety goggles on, and then click yes when you have your lab ready to go. Okay, so just click it once you have your reagents out, your glasses on, your well plate. You are going to want to have some distilled water near you just in case you need it. Make sure you have everything. Okay, don't click no. Go ahead and just click yes, because if you click no, you then can't change it to yes. So I want to know when you're ready. Okay, the distilled water, I had suggested that you guys bought some at the beginning. Ethan, if you don't have it today, it's actually not going to be used for the lab, just to clean stuff out, so you can use regular water. But if you don't have distilled water, I would recommend that you just go buy a gallon of it from the grocery store. It should be $1.25. It's not expensive, but definitely something that you will need for some of our labs. Okay, the plastic toothpicks that you guys have, you are going to need. So just click yes when you are all set to begin the lab. Make sure your safety goggles are on, and just click yes when you are ready to go. The beaker should be the 50 milliliter beaker. It's the small glass one that's in your lab. And the 96 well plate is the well plate with the smallest holes in it that you have. All right, and your safety glasses are on, so we do not have any accidents. So, here we go. Okay, I'm hoping that you guys were able to read some of the lab over before coming today. Today we have two goals. The two goals for this lab are to observe the mole ratio in simple reactions and to observe excess reactants and limiting reactants. Basically, we are going to combine chemicals in simple ratios, 1 to 1, 1 to 2, and 1 to 3. There are 3 equations listed on page 26. Those are the ratios that we are going to use. When you are doing chemistry, reagents are seldom mixed in the exact proportions of a chemical equation. One reactant is usually used up, while some of the other reactant is left over. The reactant that is used up is called the limiting reactant because it determines or limits the amount of product produced by the reaction. The reactants that are left after the reaction are called excess reactants. So today, we are going to work on this. There's a couple of different parts to this lab. We are going to do part A first, and then if we have time, we will move on to part B. When you are doing the reaction, there's a note at the top of our procedure here. It says, note, the relative amount of copper iodide precipitate may be more easily judged by the intensity of the brownish color. This is because the copper iodide precipitate settles slowly. Okay, so with that being said, a precipitate is a solid that forms at the bottom of your well plates. Okay, this lab, hopefully, you will be able to see some precipitates form. I'm going to angle my camera so you guys can see the surface I'm working on. However, I will caution you that you will not be able to see the reaction as well in my well plate as you will in yours. So, let's go ahead and get started. If we look at number 1 in A, it says, it will be easier to observe the precipitates if we use column 1. So column 1 is going down the right-hand side of your well plate. It is labeled 1. Okay, columns go top to bottom. Let me change this so you can see me, hopefully. Columns go top to bottom. Rows go right to left. So if we are working in column 1, add 1 drop of copper nitrate. So find your copper nitrate. Make sure you shake your chemicals. Okay, you want to be sure that everything gets shaken. Make sure your lid is on tight at the beginning of each and every step. So each and every step, you need to make sure you are shaking. Okay, the copper nitrate has a nice blue tint to it. So add 1 drop of copper nitrate to well A1. So that is our first one here. When I add my drops, I go straight up and down, and I have 1 drop. 2 drops to B1. So B1 is the second row in the first column. I added 2 drops there. 3 drops to C1. And 4 drops to D1. And 5 drops to E1. When you are doing labs, it is very important that you follow and put the right number of drops in the correct well plates. Otherwise, none of the lab is going to line up correctly. Once you have step 1 done, you are going to find your potassium iodide. It is a clear bottle. You are going to shake it up nice. And follow steps 2, adding the drops appropriately. You are adding 5 drops to well A1. Okay. Okay, hold on 1 second, guys. Okay, so let's see, hopefully you can see mine. So go ahead and finish step 2. Okay, now I have a reaction taking place in my well plates. It asks you in step 3 to mix the solution in wells A1 through E1 using your plastic toothpick, being sure to rinse the toothpick between times with distilled water. Now, Ethan, if you do not have distilled water, rinse it in regular water and then dry it off. If you do have distilled water, just go ahead and rinse it. Once you have all of your well plates mixed, go ahead and look at the clock. And we are going to wait 5 minutes. Okay, now we are going to, once we have everything mixed, we are going to let this sit. Okay, we have to let it sit for 5 to 10 minutes. So, when your solutions are mixed, when your solutions are mixed and you are on step 4, which is to let it sit, go ahead and click yes for me. Okay, Savannah, I know you are going to do it after class, so we're not going to worry about timing yours. Okay, so it's 1:03 on my clock. So take your solutions, and we're just going to leave them right there. Don't do anything with them. Okay, we're not going to look at anything right now, Ethan. We're going to let them sit for 5 to 10 minutes, and then we're going to make our observations. While we're letting them sit, we're going to go ahead and we can fill in our data table, and we can start moving on. Okay, so step number 5 says fill in table 4.1 with the number of drops of copper nitrate and potassium iodide in wells A1 through E1. So the drops of copper nitrate in A1 was 1, in B1 was 2. Your data table is on page 29. The drops of copper nitrate in C1 was 3. The drops of copper nitrate in D1 was 4, and in E1 was 5. Now we are going to head and do the drops of potassium iodide. In well A1 it was 5, B1 4, C1 it was 3, D1 it was 2, E1 it was 1. So your data table should look something similar to that. In step number 6, it says calculate the ratios of copper nitrate to potassium iodide in the respective wells. So this is going to be where we need to figure out a ratio. So the ratio of copper nitrate to potassium iodide in well A1 is 1 to 5. How did we know that? We have 1 drop of copper nitrate to every 5 drops of potassium iodide. Simple enough. Now in B1, the ratio is 2 to 4. Now the nice thing about ratios is we want to reduce them if we can, just like you would reduce a fraction. So the ratio 2 to 4 can be reduced to 1 to 2. Now in C1, our ratio of copper nitrate to potassium iodide is 3 to 3, or 1. Okay, so here is what my data table looks like so far. Now we are going to do our ratio for D1. Our ratio is 4 to 2. That can be reduced to 2 to 1. And then we are going to do a ratio for E1, which is 5 to 1. So data table 4.1 should be all filled out, whoopsies, except for our bottom row. I'm going to try to make sure you can see this. Raise your hand if you have any questions on how we determined the ratio of copper nitrate to potassium iodide. Okay, if you look at your wells, I don't want you to do anything with them right now. You certainly can look at them. But it has not quite been 5 to 10 minutes yet. It's been 3 minutes on my watch. So just take a look at them. What we are eventually going to do is see if we can find a precipitate, which is like a little bit of material that has settled to the bottom. Okay, it precipitates very slowly. Do not shake your well plate at all. If you want to get a better look at your well plate, you are going to be best off, and I'm going to move my camera again, getting down next to it and looking at it from the side. Mine have absolutely no precipitate in any of them yet. And some of them are going to get precipitate. So what we're going to do is we are going to go ahead and we are going to switch to part B. And we are going to let our part A sit. Part B is very similar to part A, except instead of using the first column, number 1, we are going to do the last column, which is number 12. So the side all the way on the right-hand side of our well plate. So what I would love for you guys to do is go ahead and do the steps to part B of this lab until you get down to step 10. So you're going to do 8, 9, and 10. I'm going to put my camera so you can see me doing the lab. Make sure that you shake your bottles. Okay? So go ahead and do steps 8, 9, and 10, please. Okay, right now I'm stirring my wells, making sure I rinse my toothpick between each stir. My stirring is complete. Oh, my screen went blank. Okay, and now I am at the end of step 10, and I'm going to let it sit. the water in the beaker, Ethan, is just to rinse your toothpick. You don't need any water other than rinsing your toothpick. Okay, so now we are letting everything sit. Now by my watch, our first column A, has been sitting for 10 minutes. So what I'd like you guys to do is go ahead and take a look at it. Now if you look back to our procedure on page 27, it says the relative amount of copper iodide precipitate may be more easily judged by the intensity of brown color. This is because it precipitates very slowly. So I still do not have any precipitate in any of my wells in A1. So what I'm going to do, and if you don't have any, you are going to do the same, I am going to judge my well that had the most precipitate as the well that has the darkest brownish color. So you are going to figure out, does well A1, B1, C1, D1, or E1 have the darkest brown color? When you do that, you are going to take, and in your data table 4.1, you are going to put an X in the correct column, or in what your data shows as correct, as the well with the most precipitate. Now, so the well that is the darkest brown. Okay. And then go ahead and click in the poll what it is for you. Was it A1, B1, C1, D1, or E1? Okay, remember, when you're doing a lab, there's not a wrong answer. When you are doing a lab, the answer is what your data shows. Both Cammie and Ethan got the same thing I did. My well with the darkest color is B1. So I have an X in my B1 black. Now, we are going to go ahead, and our table 4.2 needs to get filled in. We are going to fill it in the same way we filled it in for table 4.1. So go ahead and fill in table 4.2. Okay, and you should have a data table that looks like that for 4-2. Let's go ahead and check your table with mine. And now it's been almost 5 minutes. I don't have anything really going on. I have some precipitate in mine. My column 12. But we're going to go ahead and I'm going to let that sit for a minute, and we're going to look at the questions that have to do with Part A of this lab. Note I still have my lab goggles on because I do still have chemicals out in front of me. So we can go ahead and in number 2, on page 30, it says the wells with the most precipitate were, for Part A, it was B1. That's what we all got for our answer, so we can all have the same answer there. Okay, we're going to skip number 3. Number 4, which is the limiting reactant in wells A1 to A12? Well, the limiting reactant in both A1 and A12 actually, we can't do that one yet either because we haven't done A12 yet. So let's take a look at your wells for Part B. It's now been 8 minutes on mine. And I can see precipitates forming. Remember, the best way to do that is to look from the side at your wells. Okay, and I'm going to do the same thing. I'm going to send you a poll. This time we don't have brownish color. We just can see a white precipitate on the bottom. Okay, and what do you have for the most precipitate in yours? Very good. That is the same thing that I got. There is my data table. My well with the most precipitate was C. Great job. Now, if we go ahead and now we can go ahead and finish our questions. For Part B, it was C12. So why did these wells get the most precipitate? Well, that's a good question. Why did they get the most precipitate? It's because all of the reactants precipitated. They were able to be used. So number 4, which is the limiting reactant in wells A1 and A12? In wells A1, the limiting reactant was the copper nitrate. In well A12, it was the calcium nitrate. You know that because there was only one drop. So it limited the equation. It limited the reaction. What was the excess reactant in wells D1 and D12? In well D1, the excess reactant was copper nitrate, and in D12, it was calcium nitrate. In well D1, there was an excess of 2 drops excess of 3 drops of copper nitrate. There are 4 drops of copper nitrate and 2 drops of potassium iodide. But the proper ratio is 1 to 2. And we know that because that is the reaction with the most precipitate. So B1 had the most precipitate. So the best reaction is 1 to 2. 1 drop of copper nitrate to 2 drops of potassium iodide. Now this week your homework is going to be a little bit different. We are not going to do a lab write-up. This week you are going to pick any lab from this lab book that is not a lab we are doing on your syllabus. Okay, so you all got the syllabus in the beginning of the year, which had all of the labs written out that we were going to complete. For your homework, you are going to pick any other lab in this lab book. You are going to complete the lab at home. And you are going to write the lab report up for that lab. So basically, you are going to do any lab in here that you find interesting, and you are going to write the lab up. Now, what I would like is I don't want a lab report like we've been writing. You guys are doing very well at them. But what I want you to do is I want you to explain what happened in the lab. So that next week in the beginning of class, you're each going to get about 5 minutes. You are going to explain what happened in your lab. You can write a paragraph up, and I will upload the paragraph so you can look and reference it. You can do a PowerPoint, and I'll upload the PowerPoint for you so you can reference it. You can take pictures as you're doing the lab. Last year I had some students who actually recorded them explaining the lab and sent me the link to like a YouTube video, and I used that rather than them presenting live in class. But what you are going to do, and I'm going to put it here, it's going to be in Moodle. You are going to pick a lab that we're not doing in class. So for example, you could not do lab number 4 because we're doing it today, or we did it today. You are going to explain your lab to me in something written. A paragraph, 5 paragraphs, a PowerPoint, or a video. And then you are going to present it to the class during the first, you're each going to have about 5 minutes, during the first 20 minutes of class next week. You're going to be graded on your presentation as well as how you did the lab. I'm not necessarily grading you on your lab results. I'm grading you on how you did the lab, if that makes sense. And I'm going to have all of the directions written out in Moodle for you. Okay, then if you're not going to be here next week, then you'll present the following week. That's fine. If for some reason you're not here, you'll present the following week. Okay, does anyone have any questions on what I'm expecting? We're going to actually do this twice. We're going to do this now, and then we're going to do it again at the end of chemistry for our last class. Okay, when you're cleaning up today's lab, make sure that you clean your well plates out soon so that the precipitate does not stay in the bottom of the well plates. You will need to keep your well plate. You will need to rinse your plastic toothpicks because you will use those again during class. Okay, anyone have any questions? All right, so we will start next week out with your presentations. If you did not turn your lab report in, make sure that I get it at some point today. Ethan, you have a question?
If we can't rinse them in distilled water, should we just wash them with soap, like dishwashing soap? And should we wash the plates with dishwashing soap?
Yeah, if you don't have distilled water, you don't even really need to use soap on it. Just rinse it out real good with water. The distilled water is just as you're doing the labs. Some of the labs want distilled water, so it's filtered. But for rinsing it, it's going to rinse, it's going to dry. Not a big deal at all. You can just use regular water. Okay, if you have questions, I'll stay on for a couple minutes. If not, you guys can go. I hope you have a great week.